Yeah, so in this video we are going to talk about recursive algorithms. So recursive algorithms are related to a concept called divide and conquer. And divide and conquer is about dividing a problem into smaller sub-problems. So we're dividing a problem into smaller sub-problems, and then we are solving one sub-problem at a time. So we are then conquering one of these sub-problems at a time. And the way how decision trees are trained or built is related to divide and conquer, and also then how we use decision trees for making predictions. And divide and conquer algorithms can be usually implemented using a concept called recursion. So this is just one way of implementing a divide and conquer algorithm. It's something called recursion. So let's take a look at what recursion means. So here's an example of a recursive algorithm that I implemented in Python. On purpose, I removed the real name of this function so that you can guess what it is doing before we discuss it. So the question for you would be, what does this function do? Maybe pause the video for a few minutes and then, maybe step through this algorithm by hand, like by looking at it and thinking about it. But you can also, implement it in a Jupyter Notebook, for example, and play around with this and see what it is doing. So assuming that you have done that, assuming that you thought about it a little bit, let us walk through it together. So this is a function that works on Python lists. For example, a list like 1, 2, 3. And what it is doing is it's returning the length of an array or of a list. How does it work? So it takes an input here, the x, and note that there are two conditions, or that it's checking for a condition here. The condition is whether the list is empty or not. If it is empty, it will return 0, because an empty list has a length of 0. That's our stopping condition. And otherwise, it's returning a 1, and it's calling itself again on a smaller input now. So if that looks a little bit abstract, let's walk through this step by step. So let's assume we start with a full list. So let's say our input to the function is 1, 2, 3. So what happens is it will check whether the list is empty or not. So clearly the list is not empty because it's 1, 2, 3. So it will go directly to the else statement here, where it will then return a 1. Let me write down the 1 here, plus 1 plus, and then it will call itself here again based on a smaller input. So we have now a smaller input, and this input is then just a 2 and a 3 here, right? So we're cutting off the first element of the list. Now we are doing the same thing again. We are now giving, let me use a different color, we are now giving this one again to the function, which then goes to the else, where we again return a 1. So let us add another one here, plus again something, and again what will happen is that it will be truncating the array. So now we only have the 3 here, and the 3 again goes to the else, and then it returns a 1 here. And then if you have a list like this, like 3, and then you call, sorry, let me do this cleanly here. If you have a list with the element 3, and then you do the indexing 1 colon, this one will return an empty list. So this empty list in the last iteration will go again to the function. Let me use maybe yellow here. So we have the empty list. We'll go to the function, check the if again, but this time it is empty, so it will return the 0. So what will happen is it will add the 0 here. And if you evaluate this expression, this will be a 3, right? So this is the function for computing the length of an array. And we are using the concept of a recursion for that. So recursion or recursive algorithms, that means that we are calling the function itself. So if we have the function called SumFun, we are calling it itself inside. So that is like the recursive nature of this function. Of course, there are many other ways you can solve this. You don't need to use recursion. So another way you can think of is just using a for loop and then iterating through the elements of the array and then just adding up one element at a time. So we have a counter, and then we are just incrementing a counter using a for loop. And actually in practice, if you have a list like that and you want to compute the length, and let's say you want to implement your own function for doing that, I recommend not to use recursion, because in Python, recursion is limited to a certain number of calling itself. So you can't just have a very long list. It would result in an error. And this is also related to the error that you've maybe seen sometime before. It's called a stack overflow, because when you are using the recursion like here, it's building a stack of the computations before it's executing that. So it's actually piling on these computations. So you can think of it, you have one computation and then you're piling on the computations, where a computation would be like 1 + 1 + 1 + 1 here. So you're piling on, and then you would evaluate the stack from top to bottom. So you would then execute everything in this manner. But if the stack is too large, so if you have too many, let's say, additions here stacked up, then there will be a stack overflow. And this is actually also related to the name of the website, Stack Overflow. Or in other words, recursion is a neat concept, like in computer science theory, but it's not often the most practical way of implementing things. So here I have another example using recursion, and here we are solving a divide and conquer problem, sorting a list or array. And this particular algorithm is called quicksort. So again, like before, we have a stopping condition here. And here the stopping condition is if the length of the array is smaller than 2, then return the array. Otherwise execute the main chunk of the code. So how does that one work? So in the quicksort case, what we have is we have a pivot, and we set that to the first element. There are different flavors of quicksort. Some flavors just pick a random element or the last element, but for simplicity it doesn't really matter here. Let's not worry about the pivot. So let's say we have an unsorted array and we want to sort it. So the first step would be setting the pivot. That's the first element in the array, and then we create 2 new arrays or lists. One is for holding all the elements that are smaller, and all the other ones is for holding the elements that are bigger than a pivot. And then we iterate through all the elements in the array that are not the pivot and check whether it's smaller than the pivot. If it's smaller than the pivot, we put it into the smaller array. So if this is true, then put the value here. And otherwise, if it's bigger, then put it into the bigger array. And then we have the recursive nature here. So then after we sorted that into the bigger and the smaller one, we again call quicksort 2 times. We call it on the smaller array and we call it on the bigger array, and the pivot is the one in the middle. So the pivot is basically one element in the sorted list, whereas smaller is something we still have to sort and bigger is also something we still have to sort. I know this concept is a little bit abstract if we just look at the code. So let's take a look at this with a concrete example that I sketched out here on the right hand side. So let's consider we have this array here and we want to sort it from small to large. So when we call the quicksort function, the first thing is we are checking the if condition, and the if condition says if the array is smaller than 2. It's not smaller than 2, so we directly go to the else, and then we assign the pivot. So in this implementation of quicksort, the first element is assigned as the pivot. So we have the pivot here. So let me draw this here. So this is our pivot. And then we make a list for smaller and bigger. So here on the left hand side, this is smaller and bigger. So here I actually already have the values inside because we do for all the other elements in the array. So 1 colon, that would be all these here to the right of the pivot. For all of these elements, we are checking whether they are bigger or smaller than the pivot. So let's walk through this. So if we have an 8 is bigger than 5, so it goes here. The 1 is smaller than a 5, so it goes here. 3 is smaller than a 5, so it goes here. 7 is bigger than the 5, so it goes here. 9 is bigger than the 5, so it goes here. And lastly, the 2 is smaller than the 5, so it goes here. Now on the left-hand side, we have all the elements that are smaller than the pivot, and on the right-hand side, we have all the elements that are bigger than the pivot. Then on this part here, we are again calling quicksort, and on the right-hand side, we are also calling quicksort again. So let's start with the left-hand side. So if we have the left-hand side, 1 is the pivot again. Here it's the first element. The first element of the array is the pivot. And then we have our smaller and bigger. And 3 and 2 are both bigger. So they are both going to the right-hand side. And there is no smaller side here. It's just empty because there's no element smaller than 1. And then what we do is we call quicksort again. Now we only have the bigger one, right? Because smaller was empty. And we pick the first value as the pivot, and then we have only a smaller element here. There is no bigger element. So bigger in this case would be empty. Yeah, now if we would then call quicksort again on the 2 and the 3, what would happen is that in this case it will return the array, because right now we have fewer than 2 elements, right? So we have fewer than 2 elements. So in this case it will just return the array itself. And then note that we have a plus here in the center. So in the previous round, when we executed the code, we had basically a quicksort of nothing, because here this was empty. And then we had the pivot, so we had the 1 here, so plus 1. And then we had quicksort on the 2 and the 3, which then later also got split into just the 2 and just the 3. So we would basically have this plus the 2 plus the 3. So in this way we have the left hand side already sorted, so this will return 1, 2, 3, which we have here. And then we would do the same thing on the right hand side. So we would again use the divide and conquer method to call quicksort on these smaller arrays until, yeah, here in this case we would have an array with fewer than 2 elements, and they get then added up together. So now we have these 2 lists with the original pivot, the 5 in the center, and then these get added up together. So we will return the sorted array. So here in this way, the quicksort method is dividing this big list into 2 sublists plus the pivot at each iteration, unless we have only 1 or fewer elements in the array. So let us now take a look at the time complexity of quicksort. In the previous slide, we have seen that the quicksort algorithm operates somewhat like a binary decision tree, right? So if we have an array like that, we pick a pivot, and then based on the pivot, we split the array into 2 subarrays. So we split them into 2 subarrays, and then we continue like that. So every time we split it approximately in half, if we have a perfectly like a randomly sorted array to begin with. So in this way, what is the number of splits in the ideal case if we have a binary split and we split it perfectly in the middle, ignoring the pivot for now? So in that case, we would have log 2 n splits, right? So for example, if I have an array of length 8, I would split it into 4 and 4, so length 4 and length 4, and then for each one I would split it again into 2, 2, and then this one gets split into 1, 1. So in this case, let me just quickly finish this. So this is just the length of the arrays, and if you then count the number of splits, it's 1, 2, 3. So this checks out, right? So this gives us the number of splits. So one component of the big O we already know is we have to operate log 2n times on these arrays. So there are log 2n levels of things going on here. And then we know for each round here, for each split, we do something. And what we do is we check each number. So number 1, 2, 3, 4, 5, 6, 7, and so forth. We check each of those against the current pivot, which we, let's say, put in the in the middle, let's say call that pivot, and we check each number whether it's bigger or smaller than the pivot in order to put them into these new subarrays. So in the worst case, or how we usually talk about this in big O complexity, we would have n comparisons. So we would have n comparisons here, then n comparisons here, and so forth. In the worst case, if we're an infinitely long list, and we do that log to n times. So in this case, the runtime complexity of quicksort would be n, because there are n elements in the array where we do the comparisons like bigger and smaller, times n, so we have n already, times log 2 of n. So this would be the runtime complexity of quicksort in, I would say, the average worst case. So why did I say average worst case? So there's actually a worst case. So here I have a screenshot of the time complexity for different sorting algorithms, because I just thought that might be interesting or useful to you, just out of curiosity to see how other sorting algorithms compare. And the reason we pick here quicksort is just because of the divide and conquer nature and the recursiveness, and it's just easy to implement in code. So if we take a look at quicksort here, it actually lists as the worst case n squared. So why is that? So that is, consider the worst case. The best case would be, of course, if the array is already sorted, but we wouldn't know that it is sorted. So both the completely sorted or the inversely sorted array would be worst cases, because consider a case where we have a sorted or inversely sorted array. Let's say we have something like 9, 8, 7, 6, right? So if we have an array like that, what will happen is then we will pick the first value as the pivot, and all the other elements will be smaller than the pivot. So we do the checks, and then we have one very big subarray here, right? The 8, 7, 6, and then an empty one here. And then when we do that, the same thing happens again. So again, we have the large subarray. Now it's just 7 and 6, and then one small one here, an empty one. And if we have a case like that, we won't have log to n splits. We would have actually n splits. We split it n times. And that will happen if we have it perfectly sorted or inversely sorted. So in this case, if we have an inversely sorted or perfectly sorted array, what will happen is that the runtime complexity is actually n squared. However, in practice, I would say that rarely happens. And also one way we can avoid that is just by picking a pivot randomly from the array instead of just picking always the first value. So then on average, in the most cases, we won't have this worst scenario. So in the average case, we would be more like the n log n. And also in the best case, we still would have n log n, because a perfectly sorted array would be actually a worst case, because we would still go through these n splits. So there's actually no better way than, let's say, the average, where we have a perfectly random array to start with. There are some other algorithms that are performing faster in the best case, for example timsort, and I think timsort is currently the one that Python implements when you call sort on a list or sorted on a list. These are two ways of sorting a list in Python, and I think Python implements timsort. Yeah, after talking so much about recursion, how is it related to decision trees, which are the main topic of this lecture? So we can express a decision tree as a recursive algorithm, and that we can do that in two simple steps. We can say like pick a feature such that when the parent node is split, if we have a parent node or a given node, and we split it into two child nodes, it results in the largest information gain. We haven't talked about information gain yet. We will do that later in this course. So just think of it as maximizing the performance at a given step. So we basically, at each step when we split a node, we try to maximize some performance measure. So step 1 would be split parent into children to maximize performance or information gain. And then the stopping criterion, remember in the recursive examples I showed you, there was also usually a stopping criterion involved. We can say that we stop growing the tree if the child nodes are pure or if we can't make an improvement. So stop if child nodes are pure or no improvement can be made. And otherwise, if we don't stop, we go back to step 1. Now, what does pure mean? So it's not a very nice handwriting here. What I meant to write was pure. So pure means that all the training examples at a given node have the same class. If you think back of the C-Lamprey example with the molecules and stuff like that, we had 2 classes, active and non-active. So if all the nodes are such that there are only active examples or non-active examples at the given node, but not a mix of the two, then we stop growing the tree. That would be one possible condition that we can use as a stop criterion. Or if we try to use the features that we have in the data set, but we can't use them in a useful way, so either way when we use them, they can't help us separating out these classes, these training examples with associated classes further. So even though we try to make best use of the features, we can't make an improvement anymore. We can't get better separation of the 2 classes. And of course, a decision tree would work with more than 2 classes. Here I'm just trying to keep it simple and just focus on 2 classes. But later on we will also see how we can deal with multiple classes. Now here is a kind of a more formal sketch of a decision tree algorithm implemented using recursion, and I will ask you also to do that in homework. I will give you a template where I implemented a decision tree using recursion, but then I removed some lines of code, and I will ask you questions, or I will ask you to fill out these missing lines of code to complete the decision tree with a recursive implementation. So how the concept works in a nutshell is, imagine that we have a data set D here at this point, and if all the examples in this data set D are from class 1, so this symbol means for all, so if the class label is 1 for all data points in this data set, so in this data set, or if all the class labels are class 0 in this data set D, then return the tree, then we stop. So this would be our stopping criterion. Remember, in the recursive algorithms we usually put the stopping criterion first. So this would be step 2. Otherwise we do a split. Otherwise we are now here, we do the split. In order to do the split, we pick the best feature, xj. So imagine there's a feature xj, which is some feature between index 1 to m, so if we have m features, so we pick the feature xj that is best at this given node. So we haven't defined what best means, and we will do that later on. So best is related to the information gain in the CART algorithm. But we will talk more about what best or what a good feature means, what a good feature split means. Right now, just assume we know for some reason what a good feature is for splitting the node. And then similar to the quicksort algorithm, we would split the node into 2 halves, but by basically checking whether the values are larger or smaller than a certain value. Here the value would be our splitting threshold, which is kind of analogous to what I showed you previously with the pivot. So we have a threshold, and this is somewhat related to the pivot that we had. So where we check whether something is bigger or smaller than. We can also say for categorical variables it can be equal to. So there are multiple ways we can check that. Or if we have a binary feature where we only have 2 values, we have a 0 and 1, we can also just simply check whether the value is 0 or the value is 1. Or in the scikit-learn example I showed you earlier, it would be like if it's smaller than 0.5 or bigger than 0.5. And yeah, similar to the quicksort algorithm, we would then check whether the feature value, if it's a binary one, for example, is smaller than 0.5. So we would have a true and a false possibility here. And we would put, for example, the cases where it is smaller, where it's true, to the left. This would be then the values 0. And the ones bigger than 0.5, we would put them to the right, which is the value 1. So the feature value 1, these would go to the right and the other ones would go to the left. In that way, that looks maybe more complicated than it really is. So we basically check whether this one is greater or smaller than 0.5. And then this is our given node, or the decision criterion at that node. And then we split it into two subsets. So we have a data set D, and we split it into two subsets, like subset D0 and subset D1. And this would be for the ones where it's true, and this is for the ones where it's false. So we create like two subsets here. And these subsets then would represent our child nodes. So here we have D0 at child node 0 and D1 at child node 1, where D0 are all the training examples at that node that have this certain criterion, and the other ones are the ones at the other node. So this is just more like a sketch of a recursion, how we can write a decision tree in pseudocode, and in the homework we will implement that, where it will hopefully also become a little bit more clear. Yeah, but there are also many questions here that we have not answered yet. For example, how do we decide which feature we would select for splitting a parent node into the child nodes, right? So that is something that we will discuss later in this lecture, like what the criterion is to measure the goodness of the split. And then there is also the question about how we deal with multi-category splits. So this pseudocode here only shows you how to deal with binary splits. However, like I mentioned earlier in the previous video, we can actually represent a multi-category split by multiple binary splits by doing, for example, one-hot encoding. Now, if we can represent a multi-category split by binary splits, another type of feature that we know exists is the continuous features. So what happens if we have a continuous feature, like real values on a real number line? How do we deal with those? Also, these we can divide into binary splits, and we will also talk more about that later. And then also related to what I said earlier with the stopping criterion, how do we know when it's a good time to stop to grow a tree? So we can, of course, use the stopping criterion that we have here, but there are also certain ways related to pruning. There are actually two pre- and post-pruning. So pruning techniques that may also be useful to consider for stop growing a tree to improve the performance. And that's another thing we can talk about later. And then there's finally also the question, what happens now if we can't perfectly separate? So if we have this scenario here, this relies on the fact, the stopping criterion relies on the fact that we can perfectly separate the two classes, but what happens if that's not possible? So that is also related to the question, when do we stop growing a tree? I mentioned verbally that we can also stop growing the tree if we can't make an improvement in the information gain, but we will learn about that also in a later lecture. So for here, just consider this brief sketch of a decision tree algorithm implemented during recursion, and also the reason why I'm showing you this here, so I can wrap up this video and by briefly talking about the time complexity of growing a decision tree. Computing the time complexity for a decision tree when we are growing it, it's actually a little bit complicated. So there's one little tip that says basically it can be shown that the optimal split on a feature, on a continuous feature, is on the boundary between adjacent examples, so training examples that have a very similar feature value for a given feature, and where the class labels are different. So how can I visualize that? Imagine you have a continuous feature like the petal length, and you sort the training examples by that feature, and then there will be some point where you have most flowers from one class here on the left side, let's say class label 0, and on the right hand side mostly flows from the class label 1. Of course, there are maybe some zeros also in here and some ones in here, but there is some boundary where we can get the optimal split, and we know, for example, that the edges are usually not that useful when we're splitting a feature. So in that way, when we sort a feature, we have an advantage. We don't have to check all the values. We usually only have to check a range in the middle here. So for growing the decision tree, sorting helps. And from the previous slide, recall that sorting is usually n log n, right? So we know we have at each splitting node, if we sort the feature, n log n time complexity just for the sorting. And then if we're a sorted feature, we can find the decision boundary more easily. Now, usually we have multiple features, right? So if we have a feature xj, j is usually a number between 1 and we say m. So let's say we have m features in our data set. In the case of iris, it would be m equals 4. So we know that if we have to do n log n sorting operations on m features, the complexity is at least m times n log n. So we have a big O of m n log n if we don't resort the features every time. So we have m sorting operations at each splitting node, right? So now imagine you have a tree, looks like that. Now, how many nodes are in that tree? So how many, let's say, how many terminal nodes do we have, the leaf nodes? So we know from a decision tree, the depth of the decision tree, we talked about this earlier, is log 2 of n, and we are assuming this is a perfectly binary tree. It's just a simplifying assumption here. So if it's a perfectly balanced binary tree, then the depth of the tree is log 2n. So that means we have so that means for each parent node we have 2 child nodes, right? So there's the number 2. So every node gets split into 2 nodes, and we have log 2n of these splits. So the number of nodes is 2 log 2n, right? Which is just n. And intuitively you can think of it like that. This is also another assumption. We grow the tree until nodes are pure. In this case even more, until each training example is a terminal or leaf node. So that's a simplifying assumption that we make to do this analysis. So we know there are n nodes here. So what I mean is, at the bottom we have n nodes if each node is one training example. So this is n nodes. However, we care more about the splitting nodes, right? So the splitting nodes are the ones that I'm highlighting here in red, rather than the terminal nodes when we do the complexity analysis, because the red nodes now are the ones where we actually do the work, right? So when we are at the leaf nodes here at the bottom, we don't have to do any work anymore. So the red ones are the ones where we actually have to run some code to split them. So these are the ones where we actually run this n log n operation. So how many of these red nodes do we have? So in total, in a decision tree, we have 2 times n minus 1 nodes in total. However, we don't want to count the ones at the bottom here, right? Because here we don't have to do any computation. So to get the number of red nodes, we subtract the number of the nodes at the bottom, which is n, right? So we subtract n, and this is then the same as n minus 1. So we have n minus 1 where we have to do the computation. So in this case, let's check out if that makes sense. So we have let me do a different color. We have n equals 8, right? And then n minus 1 should be 7. Let's count. 1, 2, 3, 4, 5, 6, 7. So this one checks out. Now what that means is that we have to repeat this sorting here n minus 1 times. And then based on big O analysis, what happens then is we have n, so let me do that like this. We have another n here, right? So if m times n times n times log n, but instead of writing it like this, it's maybe just nicer to write it like this. So m times n squared times log n would be the complexity of growing a tree if we have to resort the features at each node. However, software like scikit-learn is a little bit more efficient, so they can do caching, so they cache the sort order at each node, and then we don't have to resort, we have to sort the features only once at the parent node, and then reuse the sorting order here, right? Because if I have a feature like that and it's already sorted, yeah, then if we split it here, these subparts will also be sorted, so we don't have to resort them if we just cache this information. So in that way we can actually eliminate the n squared. Yeah, and that is the complexity of growing a tree. It's a little bit complicated, but yeah, I hope that makes sense. Now to finish up the video a little bit simpler is the querying of the tree. So again, if we have a tree like this, we know that the depth of the tree is log 2n, right? And when we query a tree, that works as follows. We start at the parent node and then we ask a question, is this bigger or smaller than a certain value, or is there a certain category value? And then we go either left or right. Let's say we go left here, then we can already eliminate the whole right side. We don't even have to worry about that. When we query, that means like when we do the prediction. And then we have the same thing again here. So we may go right here. If we go right, then we can forget about all this part here. And then again, the last decision would be this one here. So we can forget about this one. So here, what we do is we only have the number of checks equal to the depth of the tree, right? So in fact, we have 1, 2, 3 decisions. And that would be exactly log 2n, right? The depth of the tree. So if n equals 3, if n equals 8 here, then this would be 3, right? So the complexity of querying a tree is just log 2n. Yeah, and remember also in big O notation, we actually don't use the subscript, so just log n. Oh yeah, and this is already it for this video. It was again a very long video, I have the feeling. So next video we are going to talk about the different types of decision tree, such as CART, ID3 and C45. These are different types of decision tree algorithms, and we will cover that in the next video.